As we begin chapter 7, let's think about a lot of the things we've seen already. We've definitely seen the periodic table. There was a practice question where you had to decide what was similar about an element, and it showed that oxygen and sulfur were similar. Both of them are S2P4 on the periodic table. Oxygen is a gas and sulfur is a solid. So the periodic table arranges things based on electron configuration. Some of the things they'll share, some of the things will not. So we've got a lot of assigned homework here, and that's the only way I can think of you to master these questions. You have to read the question. We're going to do some of them in the course of lecture in order to think your way through and gain what, again, I call that insight in general chemistry. So what you already know that this is S, you already know that this is P, you already know that this is D, and we don't do too much about the F, but they're sitting down there, the F metals. So I need you to focus on trends in this chapter. Again, homework is not an option. You need to learn how to predict. And these may look like funny drawings at the moment, but as we work our way through the chapter, each of them is going to have a very significant. We want you to begin to think like a scientist and deepen your understanding. You know that sodium is a solid, you know that chlorine is a diatomic gas, and hopefully by now you know sodium makes a +1 ion, chlorine makes the -1 chloride ion, and comes together to make sodium chloride. Well, that's what this picture shows. It shows the little piece of sodium sitting way down here on the bottom. It shows the chlorine gas sitting in this tube. And it shows how when they come together, it's a very explosive reaction. That's really what this is, to make that lattice sodium chloride. It is an ionic solid. So if I really dig deep down, chemical change involves an electron redistribution. When I look at the periodic table, sodium has a neon core and a 3s1 valence shell. When I look at the table, chlorine has a neon core and a 3s2, 3p5 valence shell. Atoms can either gain, lose, or share electrons. Well, it's not sharing here. We are anionic. Sodium is going to lose an electron, and it is going to obtain the neon electron configuration, which is a noble gas, a full shell. Chlorine is going to gain an electron to form the chloride ion, and it is going to form the argon noble gas shell. Again, both of these result in a noble gas configuration. This is an ionic reaction. So that's what you've seen so far. If a change requires too much energy, this redox reaction cannot occur, and you're going to gain some predictive power as we move through chapters 8 and 9. Where we need to be by the end of chapter 8, you need to be able to draw this Bourne-Haber cycle. I know gasps in the audience, all right? You have learned delta H0 formation from chapter 5. It sits here, it sits here, it sits here. What you're going to learn in this chapter are the ionization energy and the electron affinity. Here is the ionization energy, here is the electron affinity. What's left is the lattice energy, and that will be taught in chapter 8. So think back to that enthalpy diagram. That's where you first saw a diagram using just enthalpies. Now we're going to add additional features to our diagram. So that's my prelude. This is the periodic table history section 7.1, and the first person to do it was a man named Dobereiner, and he proposed triads. So if you look at the periodic table, you see like the coinage metals, that's a triad. That's where this idea came from. Newlands was the second one to come around, and that was like right after Dobereiner. And to be honest, he predicted octets, and he was ridiculed. That's what happens in science so many times. Finally, in 1887, I think that's 23 years later, he was honored for having these octets. There's always been a controversy in the literature as to who really discovered the periodic table. Well, in 1869, two people were working on it, Meyer and Mendeleev. Meyer, he kind of made a little mistake. He said it was volume-based, and he also assumed that all the elements were discovered. That honestly was not true. Mendeleev, he is the one that decided it should be mass-based, and the good thing is he left blanks where no elements was found, and the format was quote-unquote used until 1960. It wasn't until 1913 that a scientist named Moseley developed the concept of atomic numbers using X-ray. When I taught the majors class, it was one of the activities we did because it really was the basis for the periodic table. So he left research during World War II to fight, and sadly he died on the battlefield at age 27. It would have been interesting to see what else he could contribute. So why do we worry about this periodic table? Well, their summer elements are the elements of life. Think about growth of your cells, transport within your body, how things are metabolized, how you can defend against disease. There are the non-metallic elements. They are the proteins, nucleic acids, and carbohydrates. And even though carbon is only 0.1% of the Earth's crust, it's in all biological molecules. You'll see the type of bonds in chapters 8 and 9. And in organic, you'll learn about the variety of chain and ring structures. In fact, this should be the first slide of the course because that's really why you're taking it, because you really need to understand the fundamentals to learn the next step. The metallic ions, they also play an important role. They give you a balance between intracellular and extracellular fluids. There are the ion channels. We know that iron 2 binds oxygen and hemoglobin to carry things through your bloodstream, and certain elements are essential for enzyme activities. So again, lots of important things that these elements do. We are giving you the chemistry perspective.